Hello fellow people that definitely want to hear me ramble on about nuclear energy for an extended period of time that must meet the requirement of, 10 minutes? Well, it looks like I'm being held academically hostage by an unrewarding and unfulfilling system that will leave me broke no matter what, because I'll either have student loan debt or debt due to not having enough education to work anywhere but McDonald's. And now I'm literally being held hostage as well. Okay, nuclear energy. You can go away now. A little bit. You can go. Leave. Okay. Let's leave. Okay, nuclear energy. Fortunately, I just did a research paper on this, so just like every Rick and Morty fan is an expert on theoretical quantum mechanics, I am an expert on nuclear energy. There are two types of nuclear energy that humanity is trying to use for its selfish goals of destroying the planet, but hopefully these will destroy it just slightly slower. The first is fission, which is when a heavy atom becomes unstable and falls apart. Just like my life. But anyways, a heavy atom like uranium or plutonium will fall apart sort of like a raindrop, and as it splits, the energy that holds the nucleons together will be released, which we can use. In this example here, an atom of uranium-235 goes through fission and splits, creating an atom of barium-139 and an atom of krypton-94, as well as 3 neutrons. While these two isotopes are the product of U-235 fission 85% of the time, scientists have identified over 200 different isotopes that can result from U-235 fission. But that's just the chemical reaction, and frankly, I probably care about it only a little bit more than you do. So in the field we have Cramdreas Umbine, the news reporter who was struck by a bolt of pure continuity errors, giving him the ability to teleport. Take it away, Cramdreas. Cramdreas? Hello, Cram?
Thanks, Andreas. I'm here in an unnamed nuclear reactor, where I'm not allowed inside because of what happened last time.
Cramdreas, that's the back of a safe.
It really is a marvelous piece of machinery. It contains some of the most advanced energy production technologies from the 80s. This one is a boiling water reactor, but there's the other kind, a pressurized water reactor. In a boiling water reactor, water is turned into steam as it passes through the core, but in a pressurized water reactor, pressurized water absorbs heat as it passes through the core and isn't allowed to turn into steam until it gets to a steam generator, where the water can fly away and become steam. Inside the nuclear power plant, there's a core of uranium. Not fun stuff, unless you like cancer. This uranium is only 5% U-235, which is the part that goes through fission. This may not seem like a lot, but uranium ore is actually only 0.7% U-235. The rest is uranium-238. Uranium-238 is non-fissile, meaning that it can't maintain a fission reaction. The process that increases the amount of U-235 is called enrichment, and enriched uranium is what is used in a fission reactor. Around the core is a moderator, which is usually water or graphite, that slows down the neutrons that are produced by the fission of U-235, because U-235 can only absorb low-energy neutrons. There are also control rods in the core, which utilize neutron-absorbing materials like cadmium, hafnium, or boron to slow down the fission reaction. Next is the coolant, which runs through the core, cooling the core to prevent a meltdown, and also to provide water that turns into steam in the case of a boiling water reactor. Around the core is a pressure vessel that keeps all this stuff contained. Now there is the containment, a meter-thick wall of steel and concrete to keep all of this in and to keep people out. I wouldn't recommend coming here though, Andreas. The scanners keep on declining my card, even though I know there's money on there. It's not my fault that I tried to run out with my Mountain Dew and Doritos after yelling at the cashier for working at a stupid store. I mean, if someone tells me that I can't buy my Doritos, you know what I'm gonna do? I'm going to—
Okay, that's enough from him. And while he was over there, I was continuing to not care at all. So now let's get to the part that really matters.
Here comes the money!
Here we go!
So the biggest problem with nuclear energy, as well as relatively cheap to maintain, is extremely expensive to get off the ground. The capital cost of a nuclear power plant are around $5,000 per kilowatt, which is pretty expensive in comparison to a coal-fired power plant, which is about $1,000 per kilowatt. To build the Vottle 3 and 4 projects in Georgia, it cost about $14 billion, which is a lot of money. And from that statistic alone, you can see why some people would be reluctant to fund nuclear power. But there are two ways that nuclear power makes up for that. The first is that it is extremely easy to maintain, with an operation and maintenance cost of about 3 cents per kilowatt hour, in comparison to coal, which costs 20 to 40 cents per kilowatt hour. Now, the second way that nuclear fission makes up for lost ground is in how much energy it produces. Coal produces about 8 kilowatt hours from 1 kilogram, which is a drop in the Olympic-sized swimming pool compared to the 1,200,000 kilowatt hours produced from 1 kilogram of nuclear fission. This is a staggering amount of energy, and it's only burdened by the fact that uranium costs about $9.11, while coal costs about 6 cents. But because of how much energy that uranium produces, it would take $9,000 of coal to equal the amount of energy produced by $9.11 of uranium. Now you're probably thinking, what's the catch? There's always a catch, whether it be cake, free money, relationships. There is always a catch. But for this, we're going to be taking it to our correspondent in Chernobyl, Ukraine. Roman, take it away.
Haha, you thought you could get rid of me? But I will always return because I am darkness. I am death. I am the news.
How did you get there so fast? You were just at the Safeway down the street. How did you get halfway around the world in 2 minutes?
It's almost as if you don't have any friends and you're using yourself as the only character because of that. Also, I was struck by a bolt of pure continuity errors, remember? I can teleport. You literally said that like 2 minutes ago.
Huh. Well, what did you do with Roman then?
Oh, he's right here.
You killed him?
Not yet. Okay, now he's dead. But anyway, I'm here at a concession stand here in Chernobyl, and it's very uninhabitable here. While the events that occurred here are very rare, a meltdown is a very real possibility that any nuclear reactor could face. However, nuclear reactors do produce a constant amount of low-level radiation that can increase the chance of cancer and cell damage in the surrounding populace. Also, while nuclear energy is advertised as free of greenhouse gases, it does have indirect emissions, because cars and equipment that are used to make the reactors and gather materials use fossil fuels that produce greenhouse gases. But what everybody cares about are these nuclear meltdowns. Even though the Chernobyl accident was over 30 years ago, the area is still one of the most irradiated places on Earth. The residents of the area are all mutants, and I appear to be growing a third arm. Luckily, these shirts are made specifically for this, and I can say that I love Chernobyl.
Thanks, I guess? Well, nuclear energy has some good effects on the environment as well. For example, nuclear energy takes up less land mass on average than any other method of producing energy. That means less land has to be cleared, and species like the sand cat won't go extinct. Just look at that kitten. Isn't it adorable? Just look at it and tell it that it will not go extinct because we'll use nuclear energy. Also, while nuclear energy indirectly produces greenhouse gases, the process of nuclear fission actually has zero gas emissions and only solid waste. However, no matter how good fission is, there will always be one type of energy that is better. Fusion is problematic, to say the least. We don't have it yet here on Earth, and the most common place for it is in stars like our sun. The act of fusing things is combining two things to make one thing, and so it goes without saying that fusion is when you combine two atoms to make one bigger atom. Fusion must be done with light atoms like hydrogen, because anything heavier than iron will take more energy than it will produce from fusion. There are several isotopes of hydrogen, all of which can feasibly be used for fusion. But we use deuterium, hydrogen with 2 neutrons, and tritium, hydrogen with 3 neutrons, because fusion between those two isotopes occurs at much lower temperatures than any other type of fusion. This amount is still an enormous amount of heat, 100 million degrees Kelvin, or 180 million degrees Fahrenheit. This is hot enough to create plasma. Plasma is a superheated gas that causes the electrons to be ripped from the hydrogen nuclei, creating a slushy-like mass of intermingled electrons and hydrogen nuclei, all flying around at high speeds. The energy that these particles have is enough to surmount the force that repels similarly charged particles, which allows for fusion. One of the biggest problems that scientists have faced is that it takes a lot of energy to get it to this state, and so containment is difficult. While the sun has a large gravitational pull to contain all the plasma, we can't use that here on Earth, so we either have to use inertial confinement or magnetic field confinement. Inertial confinement is shooting lasers at the hydrogen, causing it to implode, generating heat and hopefully a self-sustaining burn. Confinement by magnetic fields is by far the more popular choice, and it uses toroidal magnetic fields to contain the plasma and circles it through a donut-shaped area away from the vessel walls. While we have solved this problem for the most part, the next big hurdle is achieving ignition. Ignition is the point at which fusion generates more energy than it consumes, and if this is ever truly achieved here on Earth, then the fusion reactor will essentially become a miniature sun. Test facilities like the under construction ITER plan to achieve ignition, and by 2035, the ITER facility plans to generate 500 milliwatts from 50 milliwatts. And while the facility may be expensive, totaling at $20 billion in construction costs, a single gram of deuterium and tritium can generate 500 million kilowatt hours of electricity. Also, the fact that hydrogen is extremely abundant makes the possibilities almost limitless. This is why nuclear energy is such a big deal. Fission was only the stepping stone for something bigger. Now we are so close to solving the problem of worldwide energy. Zero emissions, zero radioactivity, zero chance for the creation of a sentient race of lizard people, as much energy as you want, for however long you want it. This is why nuclear fusion is our best bet. At least until solar and wind power become cheap enough that they become better than fusion just because they don't cost $20 billion to construct.